Okay, everybody. This is an RC circuit here, a resistor capacitor circuit, and we have a very large capacitor. It's 47,000 microfarads. That's something that we'll be using for this particular experiment. We have a 10 ohm resistor hooked up to it. These are in series with each other. We have an ammeter, which actually measures how much current, how many amps are flowing around the circuit at any given time. And the power supply back here that we'll use, I'm going to crank it up, turn it on very quickly, and I'm going to record in real time the voltage across the capacitor here. Okay, it's hooked up to a computer program called Logger Pro, and I'm going to show where this curve comes from. And we'll actually derive this for RC circuits and see how we have an exponential rise. It's again voltage of the capacitor, so it's basically the charge on the capacitor. Increases exponentially, it caps off to some maximum. It looks a lot like terminal velocity right there. And then if I turn off the power, it starts to discharge. And so if your capacitor discharges, it loses voltage, and that decays exponentially as well. Okay, so I want you to actually be able to see this, the real thing, instead of just talk about it in class. Okay, so what I'll do is, let me start collecting data here. Crank up the power. So there it's charging up. Charging up exponentially, it's capping off at some maximum. It's just going to stay there. Right now the current is off in the whole circuit. I just turned the power off. And now we can see the discharge of the capacitor. Okay, the capacitor is now losing charge, it's losing voltage. If you could see it, we'd actually have some current in the circuit right here because of the capacitor is basically trying to act like a battery as it discharges. It pushes current back in the opposite direction through the circuitry. And at some point, just to be sure, I'm going to touch it with, make sure this thing's fully discharged right here. So you're seeing the exponential rise and decay of charge, the charge and voltage on the capacitor right there. What I'm going to do, okay, notice how quickly it happened. That was with 10 ohms right there. I'm going to change the resistance here from 10 ohms up to 200 ohms. Everything else is the same. And I'm going to repeat this with 200 ohms in here. Let's just see what, again, notice how steep it is. It rose very quickly to that maximum. Let's see what happens if we increase the resistance. Let me start recording. And crank up the voltage again. It's still increasing exponentially, but notice how much slower it is. So when we have real circuits that are time dependent, we have control over how fast or slow they do this. Look how it's still rising, hasn't reached its maximum yet. And if I were to discharge it, again, that too would take, that tail would be really, really long. It'd take a long time because of that increased resistance value. That's what we call the time constant of the RC circuit. It's actually the product of the resistance times the capacitance, your ohms times the farads. In this case, I increased the time constant by a factor of 20. Okay, and then it just takes a whole lot longer for things just more slowly to rise, more slowly to discharge if we turned off the power. We actually have control over how long it takes for circuits to kind of behave and do their thing. It's all these little tricks that we start to build up in modern electronics that make all your entire electronics world possible in computer technologies and things like that. So I hope this gives you a sense as to what these RC circuits are doing. We can actually see these exponentials. We'll learn the math and the theory and the derivations and everything in class. We'll do a mini lab based on exactly this setup, and we'll have some data then, okay, from what we're recording here that you can use. Okay. But anyhow, hopefully this helps, and let's dig in and try to figure out more about these capacitors and resistors.